Okay, this is the continuation of part 2, where we were going to do question 17 till the end of the paper, but the camera went fuzzy on this question, so I had to restart the software. So I explained the first part, which you can see in front of you, and I had explained the second part, but probably you couldn't read it. So I went through it, understanding how standard candles can be used to work out the distance to um, distant galaxies. So if you can find the standard candle that you know its luminosity in a distant galaxy, you can use the equation shown in the red box to work out the unknown distance, because you will know both I and L, and that's how they're used. And basically you do this for distances where you can't use the parallax method. Okay, so that's question 18 part B, so continuation of question 18 over the page, yeah, is part C. So NGC, which is a coding given to galaxies, 1357 is a spiral galaxy moving away from the Milky Way at a speed of, recession speed of 2.0 times 10 to the 6, I think it says. The spiral galaxy is such and such a distance from the Earth, that's a D, so we know the distance, yeah. Calculate the value for the age of the universe. Well, the age of the universe is basically 1 over h naught, okay? Because this is in meters per second, the velocity, and this is in meters. So h naught, to make the units balance, must be seconds to the minus 1, yeah? So if h naught is second to minus 1, that means 1 over h naught, seconds to the minus 1, will give you a value of time. So once you know the velocity and distance, you divide one by the other, you get what's called Hubble's constant, which gives you a value of 10 to the minus 18 approximately. You inverse it and you get the age of the universe in seconds, and they've given you what 1 year is in seconds, so you can divide it to get it into years. It's 1.37 times 10 to the 10 years, for 10 to the 9 is billions, so it's 13.7 billion years old. So that's a nice way of estimating the age of the universe. Okay, of course there is a big uncertainty in the value of h and all the confusion about what is dark matter and dark energy. Okay, this is a question which I noticed wasn't answered very well in the papers I marked. The energy shows that how the binding energy per nucleon varies with the number of nucleons that a nucleus has. So it's basically all the nuclei from hydrogen all the way to uranium on here, and the peak is normally iron, so that would be the peak, so iron will be around there. Iron is the most stable, so working out the binding energy, which is basically the amount of energy that holds the nucleus together, and to separate it into its constituent protons and neutrons, yeah, for iron it's the highest, therefore it will take the most energy to break up iron into its 26 protons and 30 neutrons. Okay, so iron, that's the numbers for iron. So when you go up the curve, you're producing something more stable. Okay, so uranium is lower, and uranium's value, for example, is 7.5 binding energy per nucleon, yeah, and it's given in mega electron volts, whereas the peak is closer to 8.6, and in this question they're looking at tin 50, which is 50 protons, 120 neutrons, that's about 8.5. So the difference from going from there to there is about 1 mega electron volt per nucleon. It's 1 mega, the difference between the NGs, yeah, difference in energy, is approximately 1.0 mega electron volts, but remember that's per nucleon. So if you're talking about 238, you have to multiply that by 238 to get the total energy change in uranium moving to this level, or the nucleus moving up from this level on the graph to that level of the graph. That's how much energy is required to do that, or released actually, because you're going from something less stable into something more stable. If you go to something more stable, yeah, you're basically decreasing the mass and releasing some energy into other forms. That's how you get fission, is a release of energy. Okay, so this way it will be fission, and small nuclei, this way up, will be fusion. So if you're making something more stable, yeah, you're changing mass into other and releasing the mass into other forms of energy by making something, a nucleus that's more stable. Okay? So that's the beginning of 19. We'll come back to that graph if we need to. Explain why energy is released when a nucleus undergoes fission. Well, I just explained that to you. So first of all, you've got to define fission. Fission is when a large nucleus splits into two nuclei plus 2 or 3 neutrons. So you need to have this level of detail to make sure any nasty examiner doesn't find fault with your answer. So you have to drive the point home. Yeah? Don't just say it's splitting, you have to say exactly what it is. It's a large nucleus splitting into 2 smaller nuclei. Okay? So uranium often, for example, goes into barium and krypton. That's the one I always use. And then there's a few neutrons left over, so it's usually about 3 neutrons coming out. Okay? So that's what nuclear fission is. So why does that happen? Yeah? Why is energy released? Well, first of all, you need to know what nuclear fission is. So basically, these two are more energy efficient than these. Yeah? So the mass defect, yeah, the mass, you're releasing mass. So mass is released. Yeah? So mass is decreased. So in this process, total binding energy increases. Yeah? The total binding energy increases, so energy is released. Delta M decreases, in other words. And this is where the energy comes from. So if the mass is decreased, the energy is released, so because mass goes into other forms. And this is how you work it out. Okay? So mass is decreased, and energy goes into other forms. Okay? Because it's the total binding energy increases. Yeah? And the graph shows the binding energy per nucleon. Okay? So total binding energy would be the difference in the level of the graph multiplied by the number of nucleons in the nucleus that has transformed or split. Okay, so a nucleus of uranium-238, as we spoke about, undergoes fission. One of the products is tin, as I showed you on the graph. Estimate the energy in mega electron volts released in this fission. Okay, so you need to look at your graph, and we did that, 7.5 versus 8.5. Yeah. So because we're talking about one of them is tin. So it's an estimate because we don't know what the other one is. We'd have to work out what the other one is. 120, so it'll be tin plus something x with 118 here, and that was 50, and this is 92, so that'll be 42. Okay, so if you look at 42 on there, 42, so it's the number of nucleons, so the other one is 118, is it? 118, so this one's 120, so they're both around the same level. So even the other one, this is 120, so the other one's very close to it, so both of them are around the same level here, which is 8.5 on the graph. Okay, it's like the energy level you've gone up to. It's like you've increased your potential energy, if you like. You've gone to a higher level. All right, so basically it's gone from 8.5 in uranium, from 7.5 in uranium to 8.5 in the tin value, and the other element is roughly the same size, 118 nucleons. So the gain in binding energy per nucleon is 1 mega electron, but that's per nucleon. So the increase in binding energy is 238 nucleons are now at a higher binding energy level. Yes? So all of those 238 have gone up the curve. So 238 nucleons have moved up to a higher energy level, and therefore that's the energy released. The mass is decreased if you work it out. So it's approximately 238 mega electron volts, yeah, which is approximately 240 to 2 significant figures. Okay, but I think you should keep it as 3 significant figures. All right, so that's question 18 finished. Oh no, question 18 continues. No, 19 we're on, sorry. Question 19 continues, and now they're going into fission of a different form. So this time it's strontium. Okay, a fission product. Oh, one of the fission products is strontium. That's another common fission product. Okay, so strontium 38. Yeah, 38 protons. All right. So to complete the nuclear equation, what it goes into, it tells you it's beta. You've got to get the top numbers right, adding up. 90 nucleons still remain. Beta minus has no nucleons. So, and then here, so has zero mass to 1 unit, to 1 decimal place, to 1 significant figure, and here 38 protons. Now you've got 39 protons because one of the neutrons, in effect, 1 neutron changes into a proton plus an electron. That's basically what's happening. So total number of nucleons stays the same, proton number increases, and an electron is created in this decay process. Okay. In Georgia, in December 2001, some men discovered 2 small canisters in the forest. The canisters were hot and had melted surrounding snow. The canisters, it means they're giving off energy, were later identified as containing strontium 90. Okay, so the activity due to the strontium 90 in one canister was measured as this. Okay, that's the activity. Becquerels means per second. Calculate the rate of energy release in watts. Well, this is per second, so we want joules per second. So watts is joules per second. Yeah, due to the strontium in this canister. The energy released in each decay is that. Okay, and this is how many are decaying per second. All right, so we kind of have the numbers we need. So activity is the number of decays per second, which each one of this energy. So we basically have to multiply, change this first of all into joules. So to do that, remember it's 10 to the 6, mega is 10 to the 6, so it's 0.546 times 10 to the 6 electron volts. To change into joules, you multiply by 1.6 times 10 to the minus 19. Hopefully you now know that. Okay, it's a common thing that you need to be asked in most modules. The total energy released, therefore, is the activity, which is given to us, how many are decaying per second. So it's that number multiplied by this number. Okay, the top number we just worked out. So if you do that multiplication, you'll get 113 watts. Okay, 3 significant figures. If you want to be less accurate, 2 significant figures, you can put it to 110. Okay, I didn't have enough room to write it all out, but I think you can follow that method. Okay, the authorities claimed, it says, that the canisters were 50 years old. The activity of each canister was, when new, would be this much. Okay, so we know what it would be. So that's the activity initially at time 0, and then we know the activity that they've told us was this. Okay, when it's old. So you should be able to work out using the half-life knowledge. Yeah, that they're giving you the half-life, and you know the equation to change into decay constant. Yeah, so the decay constant is this. So that's lambda. You need lambda because then you use A, which is the value we're given to at this time, and we know the A at time 0. So the only thing we don't know is T. So to find T, yeah, by taking natural logarithms. Oh, I don't know why I stopped writing. By taking natural logs, you can find T. So you take natural logs of both sides. I put A over A0 to make it easier. Once you do that, then it's equal to minus lambda T. This one also is a fraction, so you divide, you want T, so it will be minus lambda, yeah, at the bottom. This one also gives you a negative number at the top, and you'll be able to work it out. So natural logarithm of lambda over T, yeah, is what you need to do, and it comes out to 43.6 years, which is approximately 44 years. So based on the data provided, the canisters are approximately 44 years old, not 50. It's 88% accurate, so it's 12% inaccurate. So this is the kind of way that you can show that you have analyzed it to the nth degree to assess the accuracy of the claim. Okay, it's a ballpark figure. It's approximately 50 years old, but to 1 significant figure, 2 significant figures is 44 years. All right, so that's the end of the question on nuclear physics. Then there's another one coming up, and this is about penetration of radiation. The penetration of nuclear radiation through materials depends upon the ionizing power of the radiation. A teacher tested an unknown radioactive source here. He set up the source and the Geiger-Müller tube, okay, as shown. Unfortunately, currently where I'm working, we don't have one of these, so you can find an online version where you can do experiments with the source. So depending on what the source is, normally use paper, aluminium and lead to see what stops it. If it's stopped by paper, then it's largely alpha. If it's not stopped by paper but it's stopped by aluminium, then it's largely beta. And if neither paper nor aluminium stop it, then the source must be giving out gamma. The initial count rate is determined without an absorber, okay, between the Geiger-Müller tube and the source, okay. So that's like the level without putting an absorber inside it. Then they put an absorber here and see what the absorber does. So the absorber will go in between the two. When an aluminium sheet, thickness 5 millimeters, 0.5 centimeters, placed between it. So if you put an aluminium there, the source and the Geiger tube, the count rate decreased to the background level. That means it's all absorbed. So it will either be alpha or beta, not gamma, because gamma would not be affected by aluminium, but alpha or beta would be. Okay, so it could be alpha or beta based on the aluminium test. The teacher then removed the aluminium and replaced it with a sheet of paper. There was no change in the initial count rate, so it still stays the same. So it means it's not alpha, therefore it must be beta. Okay, so this is basically the logic. Explain which type of radiation is emitted from the source. You should refer to the penetration of each type of radiation through each sheet of absorber. So I have written it out for you. I've already explained it to you, so I'm going to let you struggle through my writing. Okay, so you can pause the video and go through it at your leisure. Okay, that's question 20 done. Well, first part. 20b, the count rate recorded after gamma radiation has passed through a thickness of lead is given by this equation. So this is another logarithmic equation. So if you take logs, log of r equals log of r naught minus mu x. Okay, so this is in the form of y equals c plus mx, or mx plus c, and the gradient, if you're plotting x on the x-axis, which you are, the gradient mu is negative because it's going down. So the gradient is negative, and it gives you the value mu in this equation. So they've already done a log graph. They've put r on the y-axis, and here that would be that's where you can find out what r naught is, because it's the log of r naught. It's the log of r naught is given as 540. So where r naught is the count rate with no absorber present, so that's the maximum count rate, and mu depends upon the energy of the gamma ray photons. Okay, so it's the constant of absorption, if you like. The graph below shows how ln varies with x, as I've explained, for a particular source. So once you know that the gradient is going to give you mu, you should put your values on the graph and show how to do the gradient, and you'll come up with mu being negative, and the value of 60, and it's centimeters to the minus 1, I think. Okay. Now I should have done 60 minus 50 thing because it's going down. That would give me the value. So I was saying you should reverse those. So I've done it from 540 ups against alongs, and normally that would be a positive. So I should have done 60 minus 540. Put that into there. Delta y, delta x would give you a value of minus 60. Okay, it's easy to make a mistake, so be careful, and always show you're using a large triangle to work out the gradient, because that minimizes your uncertainties. Okay, that's part B. Continues though. The graph below shows how mu depends upon the gamma photon energy. So here we worked out that mu was about 60. So we know the photon energy must be about 70. Okay, so this is a second graph, which is a correlation graph or a calibration graph. The table shows sources of 3 different elements or isotopes, and the photon energy in kilo electron volts, which is on the graph. Okay, so you've worked out mu from the first graph, as I showed you. Once you've worked out the gradient, you get a value of 60. Then you use the second graph, as I've showed you. Use second graph to find the photon energy corresponding to the mu value that you've put in. You'll see the photon energy is 70, which corresponds closest to the photon energy of xenon 133. Okay, hope that makes sense. So it's kind of 1 out of 10 out of 80 out, so it's about 12% out. Okay, so I hope that makes sense. That's the end of question. What question was that? That's question 20. So we're on the last question, question 21. In the core of a main sequence SAR, so back to astrophysics, nuclear fusion is converting hydrogen into helium. So again, that's producing something more efficient. So you will Lu delta M goes down, yeah, so decreases, and you're creating energy. Explain the conditions, however, the 6 marker. Asterisk means quality of written communication that gets the mark. So English is not your first language. You really need to find out what are the key terms. It's worth looking at the mark scheme, and this is where I've got the answers from to make sure that all the correct terms are there with a little bit of padding to make sure there is clarity in my communication. Explain the conditions required to bring about and maintain, so I've underlined the and maintain fusion in a main sequence scar. There must be very high temperatures in the core. That's where the nuclear fusion takes place. Okay, this is needed to give nuclei, the protons. Yeah, hydrogen is basically protons. Large enough kinetic energies to allow the nuclei to get close enough to each other to overcome the electrostatic repulsion forces between protons, because they're positive and positive. They will try to repel each other. So unless you have very high kinetic energies, nuclear fusion will not take place. Okay, so that's why you need very high temperatures. That will give you large kinetic energy. That allows them to get close enough for the nuclear force to interact between them. Once they get to close enough, approximately 10 to the minus 15 meters, then the strong nuclear force overcomes the repulsion force of electrostatics. Okay, so only at this distance does the strong nuclear force win out. So there must also be a high density. Now we're going to the and bit, maintain fusion. There must be a high density or pressure to maintain the rate of reaction, therefore the collisions, which will keep the temperature and pressures at the level required for fusion to sustain itself. So if you don't have enough collisions, it's not going to happen. But I think if you're going to have, if you understand star formation, protostars is basically collapsed gravitationally, and it only triggers when the pressure and the temperatures reach a high level. So that's why in astrophysics is done after you've studied thermodynamics. Okay, so that's the beginning of question 21, and now we're at the end of the paper, the last page of the paper. You'll be pleased to know a helium nucleus is a particularly stable nucleus consisting of 2 protons and 2 neutrons. Calculate the binding energy per nucleon. So binding energy per nucleon is calculated by working out the change in mass between the individual masses of the 2 protons and the 2 neutrons. So 2 times that and 2 times that is the individual masses of the protons and neutrons, and this is the mass of the nucleus once it's formed, and it should be less than 2 of these and 2 of these. So mass of 2 protons, 2 neutrons is 200, is this one times 2 plus the other one times 2, and it comes to 3755.7. Okay, so that's the mass before. The mass after is 3726. So the mass before is higher. Yeah, it's 55 to 27. Okay, the last 3 digits. So the mass change is 28.1 mega electron volt value. Yeah, and they put the c squared there because we're talking about mass. And remember, mass is energy over c squared. So it's only to show that we're dealing with mass. The value is the same, mega electron volts. So the binding energy is that. Okay, what are they asking us to do? Calculate the binding energy in joules. So we know the binding energy, the mass change, almost the loss of mass, that you've saved mass energy and you created other forms. Okay, so the mass energy released, in other words. Okay, that's what it means. So the energy released is the binding energy, but we want to work out what is the binding energy per nucleon. So whatever we work out, we've got to divide it by 4, because there's 4 nucleons that we've put into a more stable environment, helium. So the mass in joules, once we got mega electron volts, remember it's 28.1 here, but it's mega, so 10 to the 6, converted by the conversion, charge of an electron, and it comes out to this value in joules. Once you know that, divided by 4, because you want the binding energy. So this is the total binding energy, and the binding energy per nucleon, which is where it would appear on that graph we looked at in the previous question, would be 1.124 times 10 to the minus 12 joules per nucleon. Okay, so if you want 5 significant figures, is it? That's 4 significant figures. Why do I put 5? So that's 4 significant figures here, and if you want to just simplify it to 3 significant figures, which is usually more normal, then it would be 1.12. The binding energy per nucleon of helium is relatively large. Explain why this makes helium nucleus particularly stable. So binding energy per nucleon is a measure of energy required to remove a nucleon from the nucleus. Okay, well, it's actually the average energy required to remove it, because obviously the first one will be maybe different energy to remove than the second one, and the third one, and the fourth one. I don't know. So I think they're oversimplifying it slightly, but the binding energy per nucleon is a measure of energy required to remove a nucleon from the nucleus. Okay, so helium is going to hold on to it tight. If the binding energy per nucleon is large, it means a large energy is required to break the nucleus apart. Yeah, which may explain why this makes it stable. Which means the nucleus must be stable. Okay, the harder it is to remove the nucleon, which is the binding energy per nucleon, yeah, the more stable it must be. So that's the end of this 2024 run through of the January paper. So for those of you taking Unit 5 this summer, use it. Make sure you've done the paper on your own before you go through these answers, and then make improvements. And if you found the video helpful, please like, share it with your friends, and subscribe so you know when the next video will be ready. Okay, future videos will be on their way as soon as I get a chance to do them. Anyway, thank you for watching, and catch you in the next video. Bye.